So today is going to be a lecture on what's known as Ancova, or Analysis of Covariance. And it's very, very similar to Analysis of Variance, which we covered 2 weeks ago, or, well, yeah, in 2 lectures anyway. So it's a very, very similar technique. So we're going to, again, hopefully be covering sort of similar ground to what we've covered before. So nothing kind of dramatically new. Hopefully by the end of this lecture you'll have some idea of how Ancova sort of sits in the grand scheme of this linear model thing that I've been going on about for the entire module. So I'll also obviously try to tell you when and why to use it. And we'll have a bit of a look at what you get out of SPSS, although obviously that's mainly going to be covered in your practical class, but I do now, actually for the rest of the term, I do start covering some of the SPSS stuff as well in here. So by the end of today, you'll know basically, roughly, how to interpret an Ancova, and then obviously in your practical class, you'll be going over that in a bit more detail. So when and why would you use an Ancova? Well, we've seen in the last couple of weeks that you use analysis of variance, or that sort of variant of the linear model, to test for differences between means. So when you've got like lots of different groups and you want to know whether their means are different, you would apply an ANOVA. Now an Ancova is a very similar technique. It's basically kind of the same, except what you're doing is you're factoring in some other variable that is also going to influence your outcome. So, for example, when I'm not doing statistical type of stuff, I do research on what makes children scared, essentially. So I have this other life outside of statistics, hard to believe, where essentially that's what I look at research-wise. Now, also, it's possibly evident from some of these lectures at least that I quite like Doctor Who. And what you'll find with psychologists is they tend to research their own interests. So, for example, there's one person on the faculty who likes to ride motorbikes and does lots of research on why drivers in cars tend to kill people on motorbikes. I won't say anything more about the people who study addiction, but for my own part, I'm fairly neurotic, anxious kind of person, despite what external persona I may present. So I like to study anxiety, and you know, if I can mix that in with a bit of sci-fi as well, then frankly I'm really happy. So a couple of years ago I did a study, and I was trying to see, because you always see lots of stuff in the media about Doctor Who being harmful for children. So like the Daily Mail or whatever will run a headline saying, "Doctor Who, has it gone too far?" And you know, basically it's an empirical question, and it's oddly enough an empirical question that no one's really researched. So I thought I'd have a go. Turned out to be a bit more tricky than I originally thought. But anyway, so we had 2 groups who were self-selecting, a group of kids who watched Doctor Who and a group of kids who don't watch Doctor Who. So that was our kind of predictor variable, or our independent variable, the variable that we were expecting to have an effect. Our outcome variable was their sort of levels of fear after watching an episode. So we measured that in various ways. So we looked at like their, you know, whether they had nightmares. We also took some sort of questionnaire measures and things like that. But essentially our outcome was like, you could think of it as fear. So our predictor is, did they watch this particular episode of Doctor Who or not? And the outcome is fear. So that's a pretty straightforward sort of experiment. We've got 2 groups of children. We've got 1 outcome. But you would expect that, for example, the children's natural levels of fear, there are going to be individual differences in how sort of anxious they are. Some children are very shy, and you know, some children are very confident and nothing really bothers them. So there'll be sort of dispositional, temperamental differences amongst those children that we tested. We would expect that to have an effect on fear. If you're a naturally fearful kind of child, then you'd expect that, you know, your fear reaction to an episode of Doctor Who would be affected by your natural levels of fear. So if our outcome is fear, we're going to be interested also in children's sort of trait anxiety, for want of a better phrase. So that trait anxiety would be what we call a covariate. It's a variable that influences our outcome, but we haven't sort of systematically manipulated it like, you know, we have done with our sort of experimental independent variable. So we're interested in whether Doctor Who makes children scared, but in order to get a sort of a decent answer to that question, we would have to sort of factor in the children's normal everyday levels of fear. So that would be a covariate. So this is what Ancova is used for. It's when you've manipulated some kind of independent variable, so you've run an experiment, you're interested in differences between those groups of people or children in my case, but you want to factor in some other variable that you're pretty sure is going to have had an impact on whatever it is you're measuring, in my case, a fear response to Doctor Who. So, basically, that's when and why you use it. So you're still interested in looking at differences between group means, just as if you'd used an ANOVA, but you've also measured some other variable that you expect to have an impact on your outcome. So some people talk of Ancova as being a way of controlling for the effects of extraneous or confounding variables. So we could look at the impact of Doctor Who controlling for the effect that your normal sort of dispositional level of anxiety would have on your fear response. It's a bit misleading to say that you're controlling for it. You're not really controlling for it, but you're certainly adjusting for it. So you're adjusting your effect for the impact that this confounding variable might have. So that's essentially when you use it. So if you've got sort of an experimental situation, you've got groups of people, you want to compare the means in those groups, and you would normally sort of say, oh, I'll do an ANOVA, but I happen to have measured this other sort of continuous variable that I know will have an impact, or I think will have an impact on my outcome, then you'd use an Ancova instead. What are the advantages of doing this? Well, in theory, the advantages are it makes your analysis a bit more sensitive. Now, in an ideal world, by measuring a covariate or a sort of a potential confounding variable, what you're doing is reducing the error in an ideal world. So hopefully, I've got some diagrams to sort of show what I mean here. So hopefully what you're doing is some of the unexplained variance in say, levels of fear is going to be sort of eaten up by this covariate that you've measured. So what you should be doing is reducing the error in your analysis and therefore increasing the sensitivity to find an effect if there is one. So it gives you sort of greater experimental control over what you're doing. So as well as manipulating a variable in a systematic way, you're also adjusting for other factors that you know should have an influence on the outcome variable that you're interested in. So it's, on balance, it's a good thing. If you know that there are certain things that are going to affect your outcome variable and you can measure them, then it's a good thing, in theory, to factor them into your analysis. So if we have a look at an example, so remember the example from last week was looking at levels of libido, and what we had was we systematically manipulated how much Viagra different groups of people got, and our outcome measure was their libido. So we've got this sort of variability in libido. So we've already looked at this before. Remember the chocolate bar? That was like variability in libido, and we sort of we slice it up. So normally when we do an ANOVA, we slice it up into two portions. So we slice it up into the variance that can be explained by the dose of Viagra. That shouldn't say libido, that should say variance explained by Viagra. And we've got unexplained variance, so that's error variance that is just explained by things that we haven't measured. So, individual differences between people or whatever. Now, there are lots of things that can affect your libido. Medication can affect your libido. There can be medical problems that affect your libido. And in the example we're going to move on to, we also look at your partner's libido, which will affect yours, because it takes two to tango. I think there's been some kind of research somewhere in the real world, or possibly just in my head, I'm not sure, that shows that basically frequency of sexual activity is sort of quite reciprocal. So if you're with quite a sexually active person, you become more sexually active. So that would be the rationale behind measuring the partner's libido as well. Now, what you're hoping will happen is that this covariate that you measure is going to only sort of belong in the error variance. So what we're trying to do is we're trying to sort of use up some of the error variance by measuring another variable. So by measuring, for example, your partner's libido, we're hoping that, if I get my pen thing working, we're hoping that this error variance here gets smaller. So notice that the green blob gets smaller. And it gets smaller because we're using up, or we're explaining some of this error with the covariate. In an ideal world, that's what would happen. Of course, often life is not an ideal world, especially when you're analysing data, so that isn't what always happens. But theoretically, that's what you're hoping to achieve. You're hoping to eat up some of the error with this covariate that you've measured. Of course, what can sometimes happen is a little bit different to that. So we've split our variance in libido, and we've split it into like the experimental effect and the error left over. But sometimes the covariate will overlap both with your experimental effect and with the error. So this is a less ideal scenario, but it does sometimes happen. So this is why I say, on balance, it's kind of a good thing to try and measure extraneous variables and maybe use Ancova, but it doesn't always work out in quite the way you planned. So ideally, we're explaining some of the error, and that's a good thing. It will increase our sensitivity, but it can be the case that actually the covariate that you've measured overlaps with your experimental effect. So for example, in my Doctor Who example, I said that my children were self-selecting. So I had a group who would naturally choose to watch Doctor Who and a group who naturally do not choose to watch Doctor Who. My covariate was their natural level of anxiety. Now, as it turns out, if you're an anxious child, you are much less likely to watch Doctor Who than if you're a low anxious child. So we had an overlap that we didn't really want between whether you watch Doctor Who or not and whether you're a naturally anxious child or not. So in our case, the whole sort of covariate thing sort of backfired a little bit because natural levels of fear, they don't just have a relationship with like fear responses generally, they also had a relationship with our sort of experimental variable, whether the child watched Doctor Who in the first place. So this is just to make you aware that, sort of theoretically, Ancova gives you greater control and it reduces your error and all those sorts of things, but it won't always be the case. Sometimes it doesn't work out that way. So in an ideal world, you don't want your covariate overlapping with your independent variable. And you can tell whether it overlaps by if you have sort of differences between your groups on the covariate itself. So in the Doctor Who example, did we find that, the Doctor Who watching group had lower levels of naturally occurring anxiety than the non-Doctor Who watching group? If we find a sort of a difference between our groups on our covariate, then probably analysis of covariance is not the right thing to do. So there's two possible scenarios. We measure the covariate. In an ideal world, it doesn't overlap with our experimental effect, and therefore we reduce the error. We get a nice sensitive analysis. But just be aware that sometimes you'll get a situation like this on the board where the covariate isn't just eating away at our error. So it's not just kind of using up that chunk of error, but it's also overlapping with the experimental effect and sort of making that smaller as well. So just bear that in mind. So that's the logic behind Ancova and when you would use it. As I said, we've got an example which I'm just sticking to the example that we use next week, so I'm not sort of bombarding you with too much new information. So we had this example of, as I said, different doses of Viagra, they're measuring libido, and our covariate is going to be partner's libido. So that's what we've measured. So we're doing the same study, it's actually different data. So imagine we've done the study again, but this time when we did the study, we didn't just measure the libido of the person taking the Viagra or placebo pills, we also measured the libido of their partner over the same sort of period of time. So that's going to be our covariate. That's the thing we're going to adjust our scores for. Now, how does Ancova work? Well, here's just a summary of our data. So we've got 3 groups, as I said, placebo, low dose, and high dose. And these are the means of those 3 groups. So the placebo group, participants' libido is the lowest. And going up to the low and high dose group, actually their means are quite similar, and they're a reasonable amount higher. We've also, these are the means for the partner's libido, which they're not so important to register in your brain. These 3 values probably are important to register in your brain. But just to show you, the partner's libido levels are sort of vaguely in the same ballpark as on average as the participants. So to make things simple, I want to just imagine that we only have 2 groups. This just makes things a bit easier to explain. So for the time being, we're going to completely ignore the high dose group. It's gone. So we're just going to look at placebo and low dose. So the data looks a bit like this. Again, ignore that. So we're just looking at placebo and low dose groups. So we've got a mean of 3.2222, 22222. It recurs a lot. In the placebo group, and in the low dose group, we've got a mean of 4.875. If you calculate the difference between those 2, again, important note that value. It's hard to write with a mouse. So note that value, 1.653. So that's the difference between the 2 means. Now, if I were to say to you, on balance, so we're just interested, ignore covariates and things like that, we're just interested in looking at whether those 2 means are different, what test would you use? I'll give you a clue. It begins with a T. A t-test. You could use a t-test, right? All through your academic life at university, you would have been told 2 means. If you want to look at the difference between them, you do a t-test, right? So let's do a t-test. This is where I managed to demonstrate that I don't actually know how to use SPSS very well. But anyway, so here's our data. There it is. So, hang on, let me do that so it's a bit clearer. So we've got our placebo group, we've got our low dose group, and we've got scores of libido for our participants. So, right, how do we do a t-test? Compare means. Independent samples t-test. Test variable is going to be libido, and our grouping variable is going to be dose, and I've probably coded that 0 and 1. So, t-test, happy days. Okay, so we get a t-test. Now, not quite sure how visible that is. It's a big old screen and small text. So we get a t-statistic of 2.072. Note that as well. So 2.072, just ignore the minus sign. And we get a mean difference. Hang on, let me get my pen back. A mean difference of 1.653, which was the value that I just put up on the screen. So that's the difference between means. We get a t-statistic of 2.072, and is it significant? Well, it sort of isn't. So it's just about non-significant. So that's what you'd normally do, right? You're happy with all that kind of shenanigans that you do a t-test, right? If you were to have an exam question telling you to compare 2 means, you do a t-test on it. Hands up, who would do anything other than a t-test? I have to do it that way around because no one ever puts their hands up whatever I say. So if the default option is not to put your hand up, that's a winner from my point of view. Right, you'd all do t-tests. You wouldn't, for example, despite the fact that for the whole of this module I've been telling you that everything is just regression anyway, you wouldn't do a regression, would you? Because regressions are bad. You don't compare means with regressions, even though I keep telling you that you do. You think, I'm just making it up. I'm just trying to trick you, because I'm a nasty kind of person. That's exactly the sort of thing I do. I'm a statistics lecturer. I turn up, I play horrible music to you. I'm evil. So what I would want to do more than anything in the world, because I set you a nasty test as well, is I would want to trick you. So that when you go out into the world and someone says, compare means, and you go, well, I can do that with a general linear model, and they'll go, a general linear model, you imbecile. Everyone knows it's a t-test. So why would I be telling you this? Well, should we have a go at doing a regression? Because, you know, regressions are kind of fun. Now, what's going to happen if we do a regression? Now, everything you've been taught in first year, and despite everything, as I say, I've been telling you on this module, you probably believe that if you do a regression to test the difference between two means, the world will literally explode. Satan will rise from the bowels of hell and through that floor, that very point on the floor there, and he will bring chaos to the world. He will zap your computers, your screens will explode, shards of glass will fly into your eyes will pop, they'll be bleeding all down your face, your brain will leak out of your ears, and then Satan will cackle to himself, go, in a kind of satanic way that Satan would, and then he will go round the planet destroying all and sundry, and basically it will be all your fault for doing a regression when you should have done a t-test, obviously. But you know what? I'm a kind of, I don't know, I'm a carefree kind, I'm actually not a carefree kind of guy at all, but I'm going to pretend that I am, and I'm going to do it anyway. So analyze regression, I'm already trembling, I'm starting to feel the fear. Linear, right, so our outcomes, libido, we're going to predict, right, so one press of this button could bring chaos upon the world. So, shall I do it? Yeah? No? Anyone a little bit scared about what might happen? Okay, here goes.
I am Satan! You have unleashed me from the bowels of hell, and now I will destroy you all because I am a chicken!
Alternatively, not an awful lot really happened, but we did get a nice regression out of it. And you can see we have a table here. And what's in this table? Well, essentially, a t-statistic of 2.072. Basically the same value that we had when we did the t-test. And we have got a regression coefficient of 1.653, which was the difference between means. So I know I've told you this before, and I've shown you, I've put up outputs and said, oh, look, t-test and regression, it's just the same. I just wanted to, because it's quite useful to do it in this particular lecture, just show you. You can literally do a comparison between two means using different menus in regression, different menus in SPSS, and you get the same results. So what's going on behind the scenes is exactly the same. Now, why would I want to tell you that and sort of reiterate it for the sort of nth time? It's because it makes Ancova much easier to explain. If you get this basic idea that you can express differences between means as a regression or a linear model, then extending that to the sort of Ancova situation actually becomes reasonably easy to understand. So right, let's go. Let's attempt to go back to my slides, if that's possible. What slide was I on? I've completely forgotten. It was the graph one, wasn't it? There you go. Right, note. So, how does Ancova work? Well, as I said, we're just imagining now we've got two groups, placebo and low dose. And in the lecture on moderation, we had a look at categorical predictors, we had a look at dummy coding. We've also gone over that a bit in the ANOVA lecture as well. So we've seen that you can express differences between means as a regression model using this sort of dummy coding, so using zeros and ones. So notice when I had the SPSS data up, I'd coded placebo as 0 and the low dose group as 1. So this on our screen here is our model. So it's the same model I've been putting up all term. So we've got one predictor. I've called that dose, so that will be placebo versus low dose. We've got a beta associated with that. That ends up being the mean difference between those two groups. So it's the difference between the two group means. We've got a beta 0, the intercept, which ends up being the mean of the control group, so the mean of the placebo group in this case. And the outcome we're trying to predict is libido. So this hopefully is reasonably familiar stuff. So we went over it in the, as I said, the electron categorical predictors. We've also sort of whizzed over it a bit again when we dealt with ANOVA. We've also seen that when we have two groups again, we can show the model graphically, which sometimes makes it a bit easier to think about. So again, we've got our placebo group over here. So these red dots are the scores in the placebo group. We've got our low dose group, that's the sort of bluey dots there. And we can I've represented the means of the two groups with these black squares. So this is the mean of the low dose group, which is 4.875. And this is the mean here of the placebo group, which is 3.22. So our regression model, our linear model, if you like, just ends up being the difference between these two means. So the green line on here, the slope of that line is literally the difference between the two means. And you can see it's joining the two means. So that's what you get. And of course our intercept, if you like, the value of the outcome when the predictor is 0. When the predictor is 0, it's the placebo group because we've used this 0-1 coding. So the intercept just ends up being the mean of that 0 coded group. So that's all a bit of revision, hopefully. So we saw in the ANOVA lectures you can extend this dummy coding to more complicated situations. So when you've got 3 groups or whatever, again, it becomes more difficult to explain, and SPSS is doing it all behind the scenes, so I like to keep things to the most straightforward example. But you've got the basic idea that you can test differences between means using this linear model, and that's just when I ran the analysis in SPSS, that's just the output that I got from the regression. So the t-test is the same value as the t-test if you ran it through the t-test menus. This is the difference between the two group means. This is the value of the mean of the control group, the 0 coded group. So why am I telling you all this again? Well, it's because Ancova just extends this basic idea. And if you understand that basic idea, Ancova is quite easy to understand, really. Because all we're doing when we add a covariate is effectively our regression model becomes a sort of multiple regression model. So it becomes a model with an extra predictor in. And that extra predictor is going to be the covariate. So whereas before we were predicting libido from dose, and that dose variable represented the differences between group means, all we're doing, if we do an Ancova, or all that's going on behind the scenes, is the model's being extended to include this covariate. So what we had to begin with was this. So we had an outcome predicted from one predictor, etc., etc., etc. When we do an Ancova, all we're doing is we're adding in this other variable that we've measured, the covariate. And as with any linear model, any we've done this to death, we just attach a beta to it. And that beta will tell us something about the relationship between the covariate and the outcome. In this particular example, if we replace some of the letters with names to make it hopefully a bit more sense, we're predicting libido. Again, this was what we had originally, so if we were doing an ANOVA or a t-test type of analysis, we'd predict libido from the variable we've manipulated, and that variable would represent differences between the group means. So when we do an Ancova, all we're doing, we've measured partner's libido, we're just adding that in as an extra predictor. So we could, for example, literally do this using the regression menus. You don't do it using the regression menus, but you could. What's going on behind the scenes is the same. The reason you don't do it through the regression menus is simply because when you get more complicated situations, it's much easier to let SPSS go and sort of do the coding and the thinking for you. And if you do it through the Ancova menu, then it does a lot of the hard work for you. But just to prove that I'm not making it up, we go back to our data set. What we'd effectively be doing, so if we wanted to turn our t-test into an Ancova, we'll take dose out for the minute. So we're still predicting libido. Now what we want to do is adjust for the effective partner's libido. So we would stick that into the regression first. So we put that in, we sort of give it sort of, you know, first dibs on explaining the variability in libido. And then we add in the dose that people had. So our model's now got both dose as a predictor and partner's libido. And what you would end up getting out, if you did it this way, which, as I said, this is not how you do it, but it just illustrates the point that we end up with a model down here that now includes both the covariate, partner's libido, and the original effect that we were interested in. But the difference is that the original effect that we were interested in has now been adjusted for the fact that the covariate's in the model. So the original means that we were looking at have been corrected or adjusted for the levels of partner's libido that are in the model. So notice when we did the t-test and when we did the original regression, the effect of the dose of Viagra was not significant. I think it was p-value was 0.056, so it was just about non-significant. But now, factoring in the covariate and adjusting those group means for the effect that the covariates had has actually produced a much more significant result. So this is a situation where the partner's libido has basically reduced the error variance. It's managed to explain some of that error, and we've ended up with a more sensitive gauge of what the effective dose of Viagra actually is. Now, as I said, this is you wouldn't run Ancova through the regression menu normally because you'd be making your life difficult. So it has a separate menu. So you do it through the ANOVA menus actually. But I think this hopefully nicely illustrates the fact that behind the scenes, all that's going on is really quite straightforward. You've got whatever you do in an ANOVA, whatever ANOVA you're running, when you add a covariate, you're just adding in that variable. It'll have a beta value and, you know, and so on and so forth. So the basic model that we've been using the whole term stays the same. We're still using that model. It's just when you measure a covariate, you can add that in. And what I think is nice about that is you can take something, you know, like analysis of covariance that sounds hideously complicated, and hopefully see that it's really not very different to what we're doing when we do an ANOVA. We're just kind of accounting for another variable that we've measured. So it's not as hideous as it sounds. I think that's the take-home point I'm trying to make. So just to recap on all of this, what we're trying to do when we run analysis of covariance is we're trying to adjust for the effect that a covariate has. So adjust for the effect of some other variable that we've measured. And, you know, you could, I mean, all we're doing basically, or all SPSS is doing behind the scenes, is an elaborate multiple regression. So it's an elaborate multiple regression where the covariate gets put in first, and then dose of Viagra in this case, or whatever your other experimentally manipulated variables are, kind of go in afterwards. That's effectively what an Ancova is doing. Obviously, you don't have to do it in that complicated way. You can just go through a menu and you as we'll see in a minute, you just pop your covariate into a box and SPSS will, you know, worry about how to code all your groups and do all the nasty stuff for you. But the result is, the end result, the reason you would use this is because we end up getting to see the effect of an experimentally manipulated variable, so in this case the effect of the dose of Viagra, but that effect has been adjusted for whatever impact the covariate has on your outcome as well. So to return to the Doctor Who example, we could see what impact watching Doctor Who or not has on fear, adjusted for the natural level of fear in our samples of children. So there you go. So how practically do we do this? Well, as you hopefully, I don't know, it may have been too small, but from the SPSS data file, you can see you just arrange things as you sort of normally would, really. So you'd have some kind of coding variable where everyone would get a number representing which group they're in. So all these might be given a 0, and all these are a 1, and all these are 2, or something like that. The codes you pick don't matter because by doing it through the Ancova menu, SPSS will recode everything in the way that it needs to be recoded, which again is another reason for not doing it through the regression menus. But so you just code your groups here, then every participant has a score of their own libido, so this first person has a score of 3, their partner had a score of 4. So this is literally how it'll be arranged in 3 columns as you saw in the data file that I just had up. So variable representing the dose that a person received, then their actual libido, then their partner's libido. So the data looks like that. When you actually run it, as I keep saying, you don't do it through the regression menus, you would do it through the ANOVA menus. So this is the main dialog box that you'll get up. You can you put your outcome variable, in this case libido, up here. You drag your experimentally manipulated variable, in our case dose of Viagra, into that box. And as I said, there's a box down here, and that's where you specify your covariate. So I've dragged partner's libido from the list over here into there. So really the process is exactly the same as running sort of various ANOVAs. It's just that you would drag your covariate into the box labelled covariates. So it's not very complicated. If you've got covariate, drag it into the box labelled covariate. Now we talked when we did one-way ANOVA the other week, we talked about planned contrasts. Now when you've got covariates, you can't do contrasts in quite the same way as you can for a one-way ANOVA. What you have to do is use one of a set of built-in contrasts that SPSS has. So you won't be able to do every type of contrast that you might want to do. You have to stick to certain sort of predefined contrasts that are built in. Now one of them is a simple contrast, and that's what I've chosen to do here. And what that does is it compares every group to the first group, essentially. So it seems like a logical thing to do here, because our first group was the placebo group. So by selecting this contrast, I'll get a contrast that compares low dose to placebo and high dose to placebo. Now, obviously, you'll go through that in more detail in your practical class. The only other thing I want to flag here in particular is you can also select in the options to have a set of means. So if we select this variable dose here and sort of drag it into this box here. Now you might think, what's the point of getting it to display means? It's actually really important, especially for Ancova, because what it will do is it will give you a table of means that are adjusted for the effect of the covariate. So it actually gives you a table of means, and those means are the means that are actually being compared in the analysis. So they will be different to well, if you computed means in the three groups, they will be different from the means that have been adjusted for the covariate, because by adjusting them for the covariate, they change. So it's really important to see what the kind of new means are. So if we run this analysis as ANOVA, you get an output like this. The main bit of it you're interested in is this row here. So it's the effect of dose. Now, we're using all three groups now. So this is the effect of placebo, low dose, and high dose. So are there differences between those three means? And the answer is no. So we get a non-significant result. The p is 0.108. That's bigger than 0.05. So we would say that's a non-significant result. So that's without the covariate in. We haven't factored in partner's libido at all. Once we run the analysis as a covariate, we get all the same sort of gubbins that we get with a normal ANOVA. So you'd get a Levene's test if you wanted to look at that, which would tell you if the assumption of homogeneity of variance has been met. In this case, it hasn't, because that's significant. But what I want to focus on is the sort of effect of the variables that we've put in. So we've now, when we didn't have a covariate in there, obviously we only had one effect, the effect of dose. But now we have put a covariate in, we've got two effects. We've got an effect of the covariate on our outcome variable, and also an effect of our experimentally manipulated variable adjusted for the covariate. So notice now that the effect of dose, the p-value is actually dropped below 0.05. So we would now conclude that there were significant differences between the groups. Now the reason that's happened, as I said, is because the means have been adjusted for the effect of the covariate. So the means have actually changed slightly to take account of partner's libido. We also see for partner's libido that the p-value is also less than 0.05, so that would also be a significant effect. So these are both effects that are significant and we should interpret them, and so on and so forth. So how do we interpret them? For the effect of dose, we've got 3 groups, so it may be useful to look at the contrasts that we asked for. Now, because we asked for these simple contrasts, and as I said, they compare everything against level 1. Now, SPSS doesn't know how you've coded your group, so it will always tell you things in terms of like level 2 versus level 1 or whatever. So you need to bear in mind how you originally coded those groups. So level 1 is the group that you gave the lowest code to. So the way I did it was placebo was coded the lowest. So this is the level 1 is the placebo group. So I'll put P under it. Level 2, that was the low dose group, and level 3 was the high dose group, because I gave the high dose group the biggest numeric code. So again, we can just look at the significance values and also the confidence intervals, and basically 2 questions. Is the sig value, is the p-value less than 0.05? And the second question is, does the confidence interval contain 0? Because remember, confidence intervals tells us about the likely value in the population. So here it's a confidence interval for the difference between means. So if the difference between means is in reality 0, that means there's no difference between the groups. So the confidence interval, if it doesn't contain 0, what that means is the effect in the population is unlikely to be 0. In other words, it's likely to be bigger or smaller than 0. So for our contrast comparing our low dose and our placebo, the p is less than 0.05, and our confidence interval doesn't contain 0. So the lower boundary of it is just above 0, and the upper boundary of it is 3.5. So happy days, that's a significant effect, and from the confidence interval we know the effect in the population is likely to be somewhere between 0.04 and 3.5. For our high dose versus placebo, again, the p-value is less than 0.05, and again, our confidence interval doesn't contain 0. So the lower boundary of it is just above 0, it's about half, and the upper boundary is 3.88. So again, because that doesn't contain 0, we know that in the population, this effect is likely to not be 0. In other words, there is an effect there. So that's, in terms of the main effect of dose, these contrasts are useful for breaking that down. Of course, you could also do post hoc tests, and that will be fine too. If we do our post hoc tests, we can see by looking at p-values and again looking at whether the confidence intervals contain 0. So placebo versus low dose using a post hoc test is not significant. And that actually contradicts the contrast. But the reason is, if you remember when we were talking about these, I said post hoc tests, because they have to be really conservative to correct for the number of tests that you've done. So that's why, or that will be the reason why the contrasts and the post hoc tests for this comparison contradict each other, because basically the contrast has more sensitivity to find that difference. However, placebo and high dose group are significantly different. That's the same basic finding that we had from the contrasts. What we didn't get from the contrast was a comparison between low and high dose groups, and we get that here, and that's very, very non-significant. The p-value is almost 1, which means there's virtually no difference there at all. And again, if we look at the confidence interval for that effect, it does contain 0. The lower boundary is a negative number, the upper boundary is a positive number, so 0 is sort of sitting in the middle. So what that means is it's entirely plausible that there's no effect in the population. The population effect could be 0. The other thing worth noting is I told you it was useful to get a table to request a table of means, and that's what this table is here. And I don't know if you remember, but our original means were 3.22. I'm not going to remember the other ones, but it was 4 point something or other, and it's about 4.8 and 4.8, I think. These are the means adjusted for the covariate. So this original mean of 2.22 has become 2.93 through being corrected, or adjusted. Adjusted is the better word, actually. The low dose mean has changed a little bit, from sort of 4.8 to 4.7, and the high dose mean has changed a bit from, again, 4.8 to about 5.1. Let's look at that on a graph. So our original means, the unadjusted ones, as I said, 3.22, and the other two conditions were about 4.8. So when we ran our ANOVA, these were the three means that we were comparing. These were the means that we were looking at the difference between. However, when we added partner's libido in, these means get adjusted for the effect of that variable. And you can see in the placebo group, it goes down a bit. In the low dose group, the mean goes down very slightly. In the high dose group, the mean goes up very slightly. So in the Ancova, these adjusted means are the things we're comparing. So a significant effect means that there is a difference between these light green bars somewhere. So just bear in mind that you're not comparing the original means, you're comparing these adjusted means. So these are the adjusted means. So our main effect of dose, which we could report in the usual way. So we've got an F statistic. We report the degrees of freedom, its value, and the exact p-value associated with it. We could say there's a significant effect of Viagra on a participant's libido, adjusted for the effect of their partner's libido. And we know from the contrast that the placebo group was significantly different from the low-dose group, high-dose group significantly different from the placebo. What about the covariate? So we had a significant effect of partner's libido on the participant's libido. And that is, you can think of that literally, well, assuming your covariate is a continuous variable, you can think of that literally like a correlation or a regression. So it's showing a significant relationship between those two variables. So these are the data plotted, partner's libido against the participant's libido. And you can see, although it's not the nicest cloud of data I've ever seen, there is basically a slightly positive effect there. So the higher a participant's libido, the higher the participant's libido is. So again, you would just report this with the value of F, its degrees of freedom, and the exact p-value. What this basically means is there's a relationship between partners, a significant relationship between partner's libido and participant's libido. Now, the slightly unfortunate thing is when you do Ancova, there is an additional assumption that you have to test. And this is known as the assumption of homogeneity of regression slopes. Horrible name, which makes it sound horribly complicated. But essentially all it means, so we've just looked at the relationship between partner's libido and the participant's libido. All homogeneity of regression slopes means is that that relationship should be the same across our different experimental groups. So for example, if we looked at only our placebo group, we might find there's a positive relationship between partner libido and participant libido. In our low-dose group, if we looked at them on their own, we might also find there's a positive relationship between those two variables. And maybe in our high-dose group, there is too. This is what we want to see. This is an example of homogeneity of regression slopes. So the relationship between the covariate and the outcome is basically similar across the three groups. What we don't want to see is what we actually get for these data. So these are the data we've just analysed. So we get a positive relationship in the placebo group, positive relationship in the low-dose group, so they're quite equivalent. They're showing homogeneity of regression slopes. But when it comes to the high-dose group, and we get a really different relationship. So actually in the high-dose group, partner's libido is slightly negatively related to participant libido. Now, it doesn't have to be as dramatic a difference as in this example, but this illustrates the basic point that the relationship between your covariate and outcome needs to be sort of similar in your three groups. And for these data, it's not similar because it's very different in the high-dose group to the other two. How do we test for this? Well, in your lab class, you'll be shown how to basically get SPSS to look for an interaction between your independent variable and covariate. So you'll get a table like this. So it's kind of the same as before. We've got an effective dose and effective partner libido. But you'll be shown how to also add in the interaction between dose and partner libido. And if that interaction is significant, then basically this assumption is broken, as is the case here. And if that interaction is not significant, then the assumption is met. So it's all you're looking for here is that the relationship between the covariate and the outcome is the same across your experimental groups. And that interaction is testing whether that is true. So whether they are the same, so if it's significantly different, it means there's a significant difference between the relationship between the covariate and outcome across your three groups. So basically, Ancova you use to test differences between group means, but adjusting for the effect of a covariate. Bear in mind there's an additional assumption that you need to worry about, or maybe not worry, but think about, which is this homogeneity of regression slopes. Out of the analysis, you get a main effect of your experimental variable, just like you do in an ANOVA, but you also get an effect of the covariate, so there'll be something extra in the table to analyse. And you can follow up the analysis in exactly the same way as ANOVA, so you can use contrast or post hoc tests.